Welcome to LinuxConfig.org. In this tutorial, we'll demonstrate ZFS self-healing capabilities by intentionally corrupting data on mirrored drives. Warning: this demonstration uses destructive commands that will corrupt your data. Do not attempt this on production systems. We're working in a controlled sandbox environment for educational purposes only. We'll walk through 3 scenarios: single disk corruption with automatic recovery, both disk corruption with successful recovery, and both disk corruption resulting in data loss. We're working with a ZFS pool named ZFS pool, configured as a mirror with 2 drives, SDB and SDC. The pool status shows both drives are online with 0 errors in the read, write, and checksum columns. Our test file is a CentOS stream, 10 ISO image, 8.6 gigabytes in size, stored in the LinuxConfig dataset. The ZFS list command shows we're using 8.38 gigabytes with 847 megabytes available. The ls-lh command confirms the ISO file is 8.6 gigabytes. The df-h command shows the file system is 92% full, with 9.3 gigabytes total size and 847 megabytes available. Now we'll establish a baseline checksum for our test file. Running MD5 sum on the CentOS ISO file gives us the checksum ending in 8A8. For this demonstration, we only need to reference the last 3 characters, since any data corruption will change the entire checksum value. This checksum confirms our file is currently intact. We'll use this value throughout the demonstration to verify whether ZFS successfully recovers from corruption. Let's clear our terminal and begin the first scenario. We'll intentionally corrupt drive SDC using the dd command. The command writes 50 megabytes of random data to the SDC disk. We use the seek parameter with offset 1000 megabytes, which increases the chances of hitting the file data. Without the seek parameter, the command would write at the beginning of the disk, which could still work depending on where the data is stored. Now we run zpool scrub to trigger ZFS self-healing. Checking the pool status during the scrub shows drive SDC is repairing with 229 checksum errors. The scrub is 63% complete with 20.5 megabytes already repaired. Running the status again shows the scrub has completed. ZFS repaired 20.5 megabytes in 7 seconds with 0 errors. Drive SDC now shows 229 checksum errors, but the repair was successful. The pool state is online and reports no known data errors. We verify the file integrity by running md5 sum again. The checksum still ends in 8A8, matching our baseline. This confirms that ZFS successfully recovered all corrupted data from the healthy mirror drive, and our file remains intact. Now we run zpool clear to reset the error counters. Checking the pool status again shows all drives report 0 errors in all columns. The pool is fully healthy with no known data errors. This completes scenario 1, demonstrating successful automatic recovery from single disk corruption. Let's clear our terminal again and move to scenario 2. This time we'll corrupt both drives simultaneously. First, we corrupt SDC at offset 1000 megabytes with 50 megabytes of random data. Then we corrupt SDB at offset 1051 megabytes with another 50 megabytes. Notice the different offsets, 1000 versus 1051 megabytes. This creates a gap between the corrupted regions, ensuring the damaged data doesn't overlap. We initiate a scrub, and checking the status shows both drives are repairing. Drive SDB shows 402 checksum errors, while SDC shows 228 errors. Running the status again shows the scrub completed successfully. ZFS repaired 70.6 megabytes in 7 seconds with 0 errors. Both drives still show their checksum error counts, SDB with 402 and SDC with 228. Despite corruption on both drives, the pool reports no known data errors. Running MD5 sum shows the checksum still ends in 8A8. The file is intact despite both drives being corrupted. We clear the error counters with zpool clear and verify the pool status shows all zeros. This scenario demonstrates ZFS ability to recover when both mirror drives have corruption, as long as the corrupted regions don't overlap. However, this situation is risky because there was no completely uncorrupted drive to rely on. The successful recovery depends on our test having only a single large file and non-overlapping corruption. Let us clear our terminal for the last time and examine scenario 3. This time we corrupt both drives with overlapping regions. We corrupt SDC at offset 1000 megabytes with 50 megabytes of random data. Then we corrupt SDB at offset 1050 megabytes, also with 50 megabytes. Notice the overlap. SDC corruption spans 1000 to 1050 megabytes, while SDB spans 1050 to 1100 megabytes. The region from 1050 to 1050 megabytes is corrupted on both drives simultaneously. This creates a scenario where ZFS has no valid copy to recover from for that overlapping section. We initiate the scrub and check the status. This time the pool state shows a critical difference. One or more devices has experienced an error resulting in data corruption. Applications may be affected. The scrub is in progress with both drives repairing. SDB shows 403 errors and SDC shows 231 errors. Most importantly, the bottom line now reports 1 data errors, use-v for a list. This indicates ZFS detected unrecoverable corruption in the overlapping region where both drives were damaged. Using the -v flag shows detailed error information. The scrub completed, repairing 70.3 megabytes, but with 1 error remaining. Under permanent errors have been detected in the following files. ZFS lists our CentOS ISO file. Attempting to run MD5 sum on the file now returns input/output error. The file is unreadable because the overlapping corruption on both drives left no valid copy for ZFS to recover from. This demonstrates the limits of mirror redundancy. When the same data blocks are corrupted on both drives, recovery is impossible. This demonstration shows ZFS self-healing in action across 3 scenarios. Single disk corruption is automatically recovered using the mirror. Both disk corruption can succeed if damaged regions don't overlap, though this is risky with no fully clean drive. Overlapping corruption on both drives results in permanent data loss, highlighting the limits of 2-way mirror redundancy. For critical data, consider 3-way mirrors or RAID-Z configurations for additional protection. For more tutorials, subscribe and visit our website LinuxConfig.org.